Hello and welcome. So, in the last class we learnt about a few terms related to lasers like average peak and peak power, pulse energy, repetition rate, and also time bandwidth, etc., etc. And uh, we were supposed to talk about different pulsing techniques that are used in building a laser, particularly pulse laser. I just thought of discussing a few problems, trying to solve certain problems based on whatever we learned over last couple of weeks will be quite helpful before we move on. So today we are going to look at certain problems and try to solve it. Okay. So let's take the first problem. So the problem states a helium neon laser emitting at 633 nanometer makes a spot with a radius equal to 100 millimeter at 1 upon e square at a distance of 500 meter from the laser. The question is, what is the radius of the beam at the waist? Okay. So essentially the question that has been asked is to find out what is the beam waist. Okay. So you are starting, so essentially the problem, if we just draw it, so you have a laser source, so this is a laser and a beam is coming like this. Now if you go at far distance, okay, so beam will slightly diverge, right, and if you go really really large distance like 500 meters as the question suggests, so slowly the beam will grow to a larger spot size. So at the beginning, at this particular point, it would have certain value for the beam waist, while here also it will have certain diameter of the beam. Okay. So we are supposed to find out what is the beam waist. Now here you see what are the information that we already have in the question. So that is the most important thing. Whenever we come across a question, we have to understand what are the information that has been provided in the question. And the thing that has been given is that the wavelength lambda is equals to 633 nanometer, which is essentially red light, and at 500 meter distance, so whatever the distance is, there the beam will look like this, right. Now the beam will not be equally intense all over the place. So if I take a cross section of the beam, it is probably going to look like this, okay, if it is a TM00 mode or is like a Gaussian. So when the intensity decreases from this center point, so from highest intensity at the central point, it decays down as you move toward the outer side of this circle spot. When you reach the value of e square, okay, 1 upon e square, then you stop there and you collect that particular distance, you measure that distance, and that becomes your radius. So suppose this is the place where it is 1 upon e square, so this distance is my beam radius, correct, that we have learned earlier. So now we have to find out what is that value of omega 0. Now this is some beam radius, so just omega. Now how we can do that? So we have also learnt the relation between the beam waist and the beam divergence in one of the previous classes. And what was the relation? The relation was theta which gives you a measure of the divergence of the beam when theta is in radian, and that is related to the wavelength of light and beam waist as this, okay, where omega 0 is the beam waist that we are talking about. So, how do we know what is theta? Okay. So, let me first rearrange this one. So, we need to find out this omega 0 that is equal to this. Now, what is theta? So, theta is in radian. So, now if you look at this problem, so this problem if you just draw it in a very nice way. So, essentially this is your starting point of laser and the beam goes up to a distance 500. So, this is 500 meter and I have certain radius of the beam and that is this one, correct. So, I have this radius of the spot diameter here as 100 millimeter. So, here this distance, this radius is 100 mm and this have grown from the laser spot size here, and I have to find out what was that spot size, right. So, essentially this omega 0 here is essentially 100 millimeter. Okay. So, 100 millimeter means 100 into 10 power minus 3 meter, okay, and this is 500 meter. So, what will be my theta in radian? It will be very easily. So, lambda is 633 nanometer. So, that means 10 to the power minus 9 meter. You have pi and your theta in radian will be given by 100 into 10 power minus 3 meter divided by, here it is 500 meter. Okay. What we used? We used our knowledge regarding the beam divergence and its relation with the beam waist. So, let us move to the second problem. Okay. So, we are supposed to calculate the gap in frequency between two longitudinal modes in a linear cavity whose optical length is 300 millimeter. So, essentially you have a cavity and it says linear cavity. Okay. So, that is what we have discussed. We did not discuss any other type of cavities that are possible. So, essentially this distance is 300 millimeter. Okay. Now, there are several longitudinal modes that are possible, fine. Now, given this cavity length, what are the modes, and particularly what will be the gap between two successive longitudinal modes. Okay. So, and that we have to find in frequency unit. So, we know that if there are several modes that are possible, okay, what is the gap between these two, that we have already learned. If we write it as delta nu, then this is C over 2L, where L is my length of the cavity, correct. So, therefore, for this one my delta nu will be equals to C over 2 into 300 into 10 to the power minus 3. Okay. So, this will be meter per second and this will be meter. So, this will be some value in per second or hertz. Okay. So, this you can easily calculate in this way. So, let us move to the next problem. Okay. So, the question is, what is the rate of repetition, or in other words, what is the repetition rate of the pulses emitted by a mode-locked laser? The optic length of the cavity L is 1 meter. So, now we haven't talked about different types of lasers, like in terms of their you know pulsing techniques. So, right now do not worry about this term mode locked, we will be talking about it in the following class itself. So, just take it like it is a type of laser, and for this particular type of laser, what we can have is the gap between two successive pulses, okay, is given by 12 by C, and so this is essentially, there are several pulses coming, right. So, this is the gap between two pulses, correct. So, if I know this gap, then I will definitely know that in 1 second time how many times this amount of gap will appear, and that will give me the total number of repetition, or this will give me the repetition rate. So, essentially the rep rate will be 1 upon this quantity. Okay. So, you can easily solve this one. Now, the next question also, it talks about a mode lock laser. So, you can ignore this mode lock thing here. So, now the question is that this laser emits an average power P which is equal to 1 watt. The rate of repetition of the pulses from this laser is equals to 100 megahertz. Calculate the energy of each pulse. So, essentially this question asks about pulse energy. Okay. So, we know what pulse energy is. So, pulse energy is essentially, if these are the pulses as a function of time, and this is the energy. So, what is the energy of this pulse? Okay. Now, what are the information that we have been given? We have been given P average, which is equals to 1 watt, right, and it has been given a repetition rate of 100 megahertz, right. So, now in 1 second there are such 100 into 10 to the power 6 number of pulses will be there, and when the pulse is not there, there will be no light, that is this gap for between each two pulses, correct. Now, if I measure the inner energy over 1 second period of time, I will get essentially the energy of each pulse multiplied by 10 to the power 8, because there are 10 to the power 8 number of pulses in a second. Therefore, that will be my average power, because I am measuring it over a second. If I know my average power, if I know how many pulses are there, it is very easy to find out the pulse energy, correct. So, if it is P average divide 10 to the power 8, right. So, this is in second inverse and this is in joule per second, correct. So, this is my pulse energy. So, this will be 1 by 10 to the power 8, correct. joule equals to essentially 10 nanojoule, because 10 to the power minus 8 is essentially 10 into 10 to the power minus 9 nanojoule. So, this is the energy. So, most of the time it is written as 10 nanojoule per pulse. Whenever you see this, you will know that this is pulse energy that we are talking about. Okay. So, let us move on to the next problem. So, the next question says, consider a low energy level situated 200 centimeter inverse from the ground state. Okay. So, let us keep drawing. So, this is my ground state and then a low energy excited state, and this gap is 200 centimeter inverse. There are no other energy levels nearby. So, this is fairly a two level system. Determine the fraction of population found in this level compared to the ground state population at a temperature of 300 K, which is essentially room temperature. And then the value of Boltzmann constant is given, and how to convert from centimeter inverse to joule, that is also given, and Planck constant and the speed of light is also provided. So, we are simply asked to calculate the population, fraction of the population at level E. Okay. So, suppose I want to calculate population of any given state. How do I calculate? We simply use the Boltzmann distribution, okay, under equilibrium. So, for any two level, so like if I write NE as the excited state equals to Ng into e to the power minus E minus Eg over kT, right. This is very well known. Now, in our case, if I want to find out just the fraction, then if I assume that the ground state, the lower state to be just the ground state and the energy is 0, just for simplicity, okay. If you take any given energy, there is no harm, but just for simplicity, if I make Eg equals to 0, okay, assume. So, essentially my equation becomes, so, and this is for ground state, okay, and I reiterate, if you do not assume it, no problem, only thing is that you need to know the energy of that state. So, my equation becomes Ng into e to the power minus E by kT. So, ultimately what I have to find out, Ne by Ng, correct. So, this is, I have all the information. So, if I take this energy of ground state to be 0, then the excited state has energy of 200 centimeter inverse. With the given values, you can easily convert it to joule, and ultimately you find out this quantity over here. And if you do that, you will find this is approximately this, or in other word, it is 38% population that lie in the excited state. Okay. So, this problem can be also given with another level and given the lifetime of the respective states, and you should be able to find out what will be the population or fraction of population in one of these states. Okay. So, for example, like a 3-level system. Okay. So, let us look at the next question. So, consider an optical pump at 940 nanometer for ytterbium YAG crystal placed in a laser cavity. The wavelength of ytterbium is 1030 nanometer, which means that when it fluoresces, the stimulated fluorescence has a wavelength of 1030 nanometer. If all the photons emitted by pump are absorbed by the crystal and used for lasing processes, calculate the maximum power of the output. Okay, and the pump power is given by 1 watt. So, what best efficiency we can get for every photon given, you are getting output. Okay, so essentially what we say is every pump photon will lead to a laser photon. That is the best that we can have. We cannot have more than that. Okay, so in that case, if I define the laser frequency as nu L and the pump frequency as nu P, then I can easily find out that the maximum output power of the laser maximum based on this condition. Okay, so this is the maximum possible output power. So that will be given by the power of the pump. Okay, so multiplied by the energy of the laser divided by the energy of the pump that is used. So here you have been given information about all of them. Only thing is that you need to convert the wavelengths given to frequency. So power pump power is given as 1 watt. So this is essentially 1 watt, and the frequencies of the lasers. So this corresponds to lambda p, which is 1030 nanometer, and this corresponds to lambda L 940. So every information is there. Only thing is that you have to convert to particular unit, and then just calculate the number. Okay, and if you do that, you will find it is, I am just writing the final answer, is 912 milliwatt. Okay, so in this problem, you if you notice clearly, it asks for your concept, right? So whenever someone is asking the maximum efficiency, so maximum efficiency can be only when you have 100% conversion. So every pump photon is ultimately leading to one laser photon. So that is the maximum possibility. Otherwise, what do you know? Like there are thousands of photons are coming, and some of them are interacting and giving rise to even less number of laser photons. Okay, most of them are getting lost. But if we assume that there is if this is a process that pump photon is hitting and the laser photon is coming out, the quantum efficiency of this process, if it is 100%, okay, that means for each pump photon there will be one laser photon coming out. So if you have this concept clear, then the rest of the problem is really easy. Okay, so rest of the thing is just the conservation of energy, correct? Now we will consider a couple of more problems before we conclude the lecture today. So the next question is, the amplifying medium of helium neon laser has an amplification spectral band equal to delta nu equals to 1 gigahertz. Okay, so essentially we have been given the spectral bandwidth. So the bandwidth is equals to 1 gigahertz. okay, and the central frequency is 633 nanometer. And also the question says that the profile of the spectral the spectral profile is rectangular. So, you have like bandwidth is like this. Okay. So, most of the time we showed like the bandwidth is like something like this. So, here it is just like a rectangle. So, this makes our life much more simpler. And then the cavity length is 30 centimeter. Now, we have to calculate the number of longitudinal modes that can oscillate in this cavity. Okay. So, this problem we have seen, okay, during the class. So, the number of modes that can be supported by the cavity, if I call it n, then essentially is the number of times or in other word, let me tell it in a different way, like if there are say number of modes within this cavity. So, how do I find out the number of that mode? Because we know this gap, right, between two longitudinal modes, and also we know this bandwidth, that is that is something which we have to which is already provided, that is 1 gigahertz, right. So, now if we know this gap, then I will find out that how many modes are how many modes we can fit in within this envelope. So, the bandwidth is given as delta nu, and this gap between two modes is by C by twice L, correct. So, therefore, I have 1 gigahertz and C by 30 centimeter. So, that means 10 to the power minus 2 meter. Okay. So, we can easily find out how many modes will be there, which are will satisfy the standing wave conditions. Okay. So, that is the crack of this problem, that we need to find out how many modes will satisfy the standing mode condition, and if you know the expression which connects the length of the cavity and the frequency of light, and then you know that what is the gap between two such modes. Okay. So, you know nu, you know how nu is related to the cavity length, and then what is the difference between say nu 1 and nu 2. So, knowing that gap and knowing the overall bandwidth, spectral bandwidth of your laser active medium, it is extremely easy to find out how many such modes will be there. Okay. So, that is all we did. So, here last question that we will look at is if we take a Q Swiss laser that emits pulses of 10 microjoule of duration 1 nanosecond, and the repetition rate of the pulses is equal to 10 kilohertz. So, what I have? We have pulse energy, you see, you have to notice the unit, right. So, this is 10 microjoule. So, it is pulse energy, that is equals to 10 microjoule, and pulse width, the duration is this. So, pulse width is 1 nanosecond, and the repetition rate is equals to 10 kilohertz. So, 10 to the power 4 hertz. So, first thing we have to calculate the peak power. Okay. So, peak power is given by the energy of a pulse divided by its pulse width. So, essentially peak power is equal to energy of a pulse divided by the pulse width. So, here what we have 10 microjoule, right. So, divided by pulse width is 1 nanosecond. So, 10 to the power minus 9 second. So, you can easily calculate what will be the peak power, and if you do that you will see it is 10 into 10 to the power 3 joule. Okay. And you can see how much is the peak power, okay, right. So, this is sorry per second. So, this is essentially 10 kilowatt. Now, what is the average power? Now, if you know the peak power, if you know the pulse energy, okay, so you essentially have this system. So, you know this energy. Now, you know how many times such pulses will be there. So, you know the repetition rate. So, then if you multiply the repetition rate with the pulse energy, you get essentially the average power. So, P average is equals to pulse energy, that is 10 to the power 4 joule per second multiplied by the repetition rate, that is 10 to the power 4 hertz. Then, so we have to take the pulse energy which is given here, sorry for the mistake. So, essentially is 10 microjoule multiplied by the rep rate. Okay. So, 10 power minus 10 into 10 to the power minus 6 joule into 10 to the power 4. Okay. So, this gives rise to 10 into 10 to the power minus 2 watt, okay, or in other word this is 100 milliwatt. So, if I know the very basic concept about peak power and average power, then we can always find out what are the values of these quantities, okay, and how we definitely would know in that case how these powers are related to several other quantities like repetition rate or pulse energy, pulse width, etc., etc. So, today we tried to look at certain problems which are very relevant to whatever we have learned in last couple of weeks, and we solved them. So, I hope this will help you in understanding this overall topic in a much better way, as well as it will help you to prepare for your exams. So, we will come back with a new topic, that is the pulsing techniques for pulse lasers in the next week. Thank you very much.